Hello everyone. Sorry for the delay. I hope you guys are having a good morning. Uh, I guess we can get started.
Welcome to Tilde's week 3 presentation, and today we will be starting with Tech Stack, and I hope you guys are ready, and we could start off now.
Yeah, it is.
I'll start now. Hi guys, we are Team NetStack and we are building a TCP/IP stack from scratch to explore protocol implementation and networking from first principles. For today, one of our teammates is sick, Vishru, and he will be answering your doubts or questions if you have any. So I'll go with the architecture diagram. So for past 2 weeks, we are implemented the turn interface IPv4 header, and last week we are done with the ICMP protocol. And for this week, we have worked on the UDP protocol where we implemented the UDP parser, checksum verification, and the UDP response. So the green color blocks are the ones we have like this week we have done with it, and the blue ones are for the next week, the TCP part. And we are able to set up a live dashboard where we can see all the data. So I'll hand it over to Aishwarya.
Yep. So let's move on to the main thing which we worked this week. That was about UDP. So I think in week one we mainly covered about IP functions. So it's IP's function to get a packet from one machine to another. But IP stops there and has no idea about the application. It doesn't know if it's the DNS resolver or your program or any other application which is running. So let's say if multiple programs are running on the same machine and multiple packets are arriving to that machine, there's no way to know which program exactly does that packet belong to. And this gap is mainly filled by the transport layer, that is UDP or TCP. And since we went to UDP mainly this week, so let's dig deep into it. And yes, there is a reason why UDP is called User Datagram Protocol. So if you split it, then user as in it just refers to user process or application like DNS server or video call app or any other application. Well, datagram is a scientific term which is a self-contained packet of data which acts independently. So let's just say that a part of like few packets or a packet is corrupted, then it wouldn't affect the other packets. This is what it means. And protocol is just simply set of rules which are followed by both sender and receiver. So in simple words, UDP works by adding port numbers, which acts like an extension. Implementation. One of the most interesting aspect of UDP is that it's intentionally minimal. So in implementation, the first part was passing the header. Its header is correspondingly very simple. It consists of only four 16-bit fields, making the total header size a fixed 8 bytes. So the orientation consists of source and destination ports where the packets are coming and where they're going, and then a length field to determine the UTP datagram's boundaries, and then a checksum part to verify the integrity. And if you guys notice, then there isn't really a field for IP address. And yes, this does create a huge problem for us. So the most interesting part in implementation, like the most challenging too, wasn't really passing the header, but then it was actually implementing the checksum verification, unlike last time. So since UDP doesn't really have UDP's header doesn't really have IP address, let's just say if the destination IP gets corrupted during transmission, then our UDP checksum would still be valid and it would still be going to the wrong IP address. And that's really wrong. So that's when UDP comes up with this conclusion that it would have another header, which is pseudo header, which would contain the source IP, destination IP, and then the initial checksum set as 0, protocol so that we don't change UDP and TCP while transmission, and UDP length. And yes, this doesn't get transmitted and only exists during checksum calculation. That's why it's pseudo header. So this is how it's performed is that checksum calculation is done twice, and pseudo-header is made twice, once at the receiver end and once at the sender end. So by checksum would calculate for all these three parameters, pseudo-header, UDP header, as well as the data which we are storing, which is obviously in variable length. And the same thing would repeat again in the receiver end. And at the end, if our output would be 0, that is after one's complement, then it would be considered as valid. To dig deep into the flow, once the UDP packet is received from the TUN interface, the first step was to pass the UDP header. From this, we reconstructed the pseudo header, which using the IPv4 source address, destination address, and other fields like protocol number, UDP length, and combine it with the UDP header and payload before performing the once complement checksum. And then we compared our computer checksum against the Wireshark's computer checksum for the same packet. And more about this will be explained in next few slides. Later, well, we did face a bug where the UDP length field in the pseudo header was being used in host byte order instead of network byte order. And we were actually stuck with this for like a lot of time since it's supposed to be in network byte order. We use the basic conversion functions, htons and the other one to convert it back. And this is how we actually finished the match with further checksum. Moving on to the terminal output, I would like to hand it over to Vansh.
Yeah, so I'll explain the terminal output part where we'll see all this add up in the dashboard. So as you can see, I have opened two terminals over there. On the left, we have the live dashboard, and on the right, where I have like set up the turn interface. Then I have sent a ping request where I have sent ICMP packet, and on the left we can see different metrics over there. One is for the different protocols, ICMP, UDP, and TCP. Then we have received packets, received bytes, transmitted packets, and bytes. For now, we are yet to implement the transmission logic. So once we are done with that, we'll surely implement and show it over here. Then below that, we have drop diagnostics, which are like filtering out the non-IP4 traffic, bad checksums, unknown protocols, or malformed headers. So for sending the UDP packet, we have used a tool called netcat. So you can see that over there on the arrow, where I have sent a string called netstack as a payload for the UDP. Then I have set a flag for UDP. Then the destination IP and the port is 53. So that port is the standard port for DNS. And as you can see then on the dashboard, it is able to receive the two packets of UDP and which is equal to 52 bytes. So I'll break that math down for you. So the first packet is of 36 bytes, which is 20 bytes of IPv4 header, 8 bytes are of the UDP header, which are the destination port, source port, then the length and the checksum part, which are 2 bytes each. Then there is the 8 bytes of payload, which is dynamic. For now, I have used the string called netstack, so those are exactly 8 characters, so those are equal to 8 bytes for now. Then the remaining 16 bytes, the next UDP packet is sent by the netcat, so that is actually the OS flush, which is used to close the UDP connection. Yeah, so I'll explain the Wireshark part. Yeah, so this is the screenshot for the Wireshark capture. So on the left side, you can see the details of the Wireshark capture over there. On the right, you can see the highlight, it's highlighted in the blue, the UDP capture over there. You can see the source IP, which is exactly the same which we set for the turn interface. The destination IP is the same we used for the netcat command. Then protocol is DNS because we used the port 53 to send the UDP packet. Then on the left part, you can see all those UDP payload is exactly 8 bytes, which confirms what I said. And on the right side, there is 36 bytes of wire, like the exact length of the packet is 36 bytes. So the first packet which we sent from the netcat. And then there is a red color error over there, which you can see malformed packet DNS. So that is basically Wireshark expecting a standard DNS query. Since we used port 53 for sending UDP packet, Wireshark was expecting a standard DNS query which will be formatted in the binary format what it expects to be. But since we sent a ASCII character instead of the binary format, it is showing as malformed packet, which is actually not an error. It's a sign, like it's a great sign for us, because we can like we are not relying on the operating system to format the data for us, and we can like manually capture and manipulate the UDP packet from our side. For next week, so for next week's agenda, we'll implement the TCP protocol and then the state machine and live tracking. We'll implement TCP three-way handshake and we'll establish reliable connection using the three-way handshake, the SYN, SYNAC, and the acknowledge stages. Then we'll implement the state machine, then data reception, where we'll process the actual application data once the TCP connection is fully established. Then we will update all of this in the live dashboard where we can monitor the data and we can show it to you guys. Yeah, that's it for from my side. If you guys have any questions or doubts regarding this.
Hi. I just had a quick question. You mentioned something about turn servers, I believe, right?
Yeah,
You guys are using turn servers?
yeah, we are using an interface. It's a virtual interface for like routing the packets to our C
Okay.
code.
Oh, that's very interesting. I remember like during one of the projects that I worked on, it was pretty tough to find, turn servers that you can use for free. How did you guys get about it?
No, no, like it's like like it's built in the Linux. Like it's a virtual thing, I guess. Like it's not something on the internet. Like we just assign a virtual turn interface, so it will act like it will route all the traffic to that device instead of the standard Wi-Fi, Ethernet, or other port.
Right, right. Okay. Okay,
We
cool, cool.
use turn devices. Like we set
Right.
it as turns. Yeah.
Okay. Thanks.
I think Arjun was asking about the turn servers and not the turn device. Yeah.
Oh, I don't think we use that. We use turn device.
Yeah, yeah. I figured that out after you guys responded. Thank you.
If there are no questions, I think we can move on to the next team. That's Mushroom. If you have any further questions, you can feel free to drop it in the chat.
Can the next team proceed? My other mentee is not here.
After the one after Mushroom.
Yeah.
Oh, all right. Okay then. So let's start with Ziguana right now.
Hello everyone. So we are Team Zigyana. We will be speaking about our week 3 progress. The mentees are Abhishek, Aniket, Arnav, and Tanishq, and the mentors are Ashton and Sankhya. Could you go to the next slide? Okay. So we will be speaking about the Lexa first. So this part was supposed to be covered by my teammate Tanishq, but he's not here right now, so I would be covering it. So the Lexer is the first phase of our transpiler. It converts raw source code from a toy language into a clean stream of tokens, stripping out white spaces, comments, and identifier keywords, the strings, numbers, and so on. It also uses one character lookahead to catch two character operations like plus equal to and minus equal to. At the end, each token comes out as a struct containing its type, its value, and its exact line and column position. There are a few things missing from our lecture, so this week we added two of them, error handling and string interpolation. Could you go to the next slide? Okay. So error handling is a crucial part of any lecture. It prevents crashes, gives user precise feedback with the exact location of their mistake, and supports batch reporting. We can show a full list of errors at the end instead of stopping at the first one. We implemented this by detecting a bad token, an unterminated string, or a missing closing braces, marking it as invalid, storing its location, and counting to scan, continuing to scan rather than stopping. Moving on to the string interpolation. Could you go to the next slide? This is an important feature in any language since it lets programs insert variables directly into the string, right inside print statements instead of relying on long string concatenation. It also makes output message far more expressive. We achieved this by switching the lexer between a normal mode and a string mode, splitting each string into literal text segments and the variable part inside the parentheses. Over to Arnav. Thank you.
So now I'll be speaking about a parser, which is the first stage of a transpiler that understands the source program's logical structure. So a parser is known as a recursive descent parser. It's a top-down type parser. So basically, it parses the input by recursively calling a set of parse function for every non-terminal in a grammar. So using this, parser constructs an abstract syntax tree, and the main job of the parser is to generate a structured representation for code generation and also for this checker. So I'll pass it over to Abhishek to explain the AST.
Sure. So the AST, the abstract syntax tree, is how we turn source code into a structure we can actually reason about programmatically. Instead of just a flat string of tokens, it's made of nodes, and we split those into two categories: statements. These are with do something like a variable declaration, an if statement, or something like a while loop. And expressions, on the other hand, are like they evaluate something like a binary operation like a plus b, or function calls, literals, anything of that sort. Each node type is its own struct with the fields it actually needs and the position data. The parser is what actually builds the tree, walking the token stream and constructing the nodes. I now would be speaking about the parser flow from here. Thank you.
Thanks. So this slide shows the overall structure of a recursive descent parser. The entry point for parsing every source file is the parse program function, which determines whether the next construct is a function definition or a global statement, and it dispatches the appropriate parser function. So let's take an if statement for an example. When the parser reaches an if token, parse statement recognizes it and calls a parse if statement. And then parse if statement, the function first parses the condition by calling parse expression, and then parses the body by calling parse block, and which repeatedly invokes a parse statement to parse every statement inside the braces. This recursive structure allows nested blocks and control flow statements like if and while statements to be handled naturally. Whenever an expression is encountered for like an assignment or a return value, the parser follows the expression parsing chain shown on the right. So each function is responsible for a single precedence level. Yeah, can I get the next slide, please? Yeah, so now I'll talk about expression parsing more in detail. So expressions are passed differently from statements because you have to respect the operator precedence. Instead of a single parsing function for expressions, we divide the work into multiple parsing functions where each function deals with a particular precedence level. At the top, we have parse expression, which calls parse equality, and then equality calls comparison, comparison calls term, term calls factor, factor calls unity, and finally unity calls parse primary. Parse primary handles literals, variables, group expressions, function calls, and array accesses. So each of our parsing functions follow exactly the same logic. So first it calls the next higher precedence parsing function to parse the left operand, and then it enters into a loop to check if the current operator belongs to its own precedence level. So so if it belongs to its precedence level, then it finds the next one. So it parses the right operand by calling the higher precedence function, and then it creates an AST node with the respective operator and both the left and right operands. And this repeats until there are no more operators of that precedence in that expression. Can I get the next slide, please? So for example, when parsing the expression a plus b multiplied by c, parse term first parses a and then encounters the plus operator. So it parses the right hand side by calling parse factor. And since parse factor is responsible for multiplication and division, it consumes b multiplied by c and returns that AST node. Finally, parse term creates a plus AST node using a as the left child and the multiplication AST node as the right child. Because higher precedence functions finish before lower precedence ones create their nodes, the resulting AST automatically reflects the correct operator precedence. So as you can see from the AST print output for this program, the binary node of multiplication is a child of binary node of plus. So I'll pass it over to Abhishek to explain the checker.
Sure. So once we have got a tree, having the right shape isn't enough. It also has to be semantically valid. That's what the checker does. A separate path that runs after parsing, walking the same AST, doing scope resolution and type checking. Two structures drive this. First, a function signature table. So this is a hash map from function name to its return type and parameter types. Built in one upfront pass before we check any function body. That's what like lets function call each other regardless of the declaration order. Second is variable scoping, a stack of hash maps, not one flat map. Every block we enter pushes a new scope. Every block we leave pops it. Lookup search from the innermost scope outwards. So inner declarations correctly shadow the outer ones. And once a block ends, its variables are gone, like it's destroyed. Actual checking is two recursive functions, one for statements, one for expressions. Mirroring the tree structure, the expression checker infers and returns a type for everything it visits, so a parent node can validate against it. That's how we catch things like mismatch operand types, um, or a wrong initializer. We also track the current function's return type as we walk into it. So every return statement gets checked against that, including like void function violation. When something's wrong, we don't crash. We like record the exact line and column and keep walking. So one checker run can surface several errors at once. The whole point of this is that by the time code reaches code gen, we already know it's structurally sound. So speaking about code gen, Aniket would be speaking about it. Thank you.
Thanks, Abhishek. So I'll take you to the final phase, which is the C code generator. So basically, once the parser gives us a validated AST, we just literally turn that tree into actual C code. It's a single pass system, and we take the AST, walk it node by node, and recurse into it. So deeply nested code is just handed automatically. It applies translation rules, does lookups for types and operators, and just streams it to a buffer. It auto tracks the indentation, adds the code upfront, and yeah, you get a complete C source file. Um, so the architecture here is really simple. It is just one straight traversal. It maps all our types, int, bool, string, directly to the C equivalents, handles loops, functions, arrays, all of it. But really, the critical thing is the correctness, right? So we auto parenthesize the output to guarantee the math is grouped right. We also do safe string escaping and we force strict C void for empty functions. That way, the C compiler will literally catch your errors at the call set. It's extremely minimal and only includes the libraries you actually need, so there is no bloat. If you look at the slide, you can see it in action here. So the source code actually goes in A plus B into C grouping being handled safely right here. So, looking at week 4, our main focus is just finishing any remaining features like the string interpolation and print function for the code generator. And we will also go hardcore on testing for the lexer, the parser, and the generator, and obviously getting the final documentation right for our language. So, yeah, that's it from Team Zigona. Thank you.
Are there any questions for Team Ziguana?
Yeah, I actually, can you guys hear me?
Yeah, we can hear you. Go ahead.
Could you just present your slides and go to the parser flow slide, please?
Yeah, 1 second.
Yeah. Okay, and could you go to the next one as well? Okay, so I don't really have much of a question. It's a little bit of feedback on your slides. Uh, from what we look for in presentations and what slides are supposed to be, is more like it's mainly just there for the audience to refer to while you guys are explaining. So if the audience gets lost for like 5 seconds, they can look at the slides and connect back into the flow. But I find these two slides a little too complicated and verbose. So I feel like if someone gets lost and looks at this, they can get more confused because they're not really sure where to follow. That's just a little feedback on the slides. I hope I was clear about it, and I hope I was audible the entire time. My internet has been shaky today.
Yes. Okay. Thanks.
Yeah, yeah. We'll take the feedback. Yeah. Th-
Yeah,
We'll work on it the next time.
cool. Thanks, guys.
And any questions?
If there are no questions, we can move on to barely learning.
Everyone, we're team Barely Learning and we're here to present our week 3 progress. So our objective was to create a model to play the Donkey Kong game using imitation learning and the actor critic reinforcement learning. Now to simplify the problem, we're recreating only the first level of the game, in which there is 7 actions for Mario, and each and every barrel has only a 50% chance to roll down the ladder. Now, this introduces a factor of randomness. So now the model cannot simply memorize a sequence, but it has to actually learn the patterns and find new strategies to win the game. Next slide, please. Our implementation is based on this paper that is learning to play Donkey Kong using neural networks and reinforcement learning. Now, in the paper, we recreate the game environment, and then the paper trains the AI agent using an MLP based actor critic model, along with the learning from demonstration, which is also the imitation learning. Now, instead of feeding in raw images, it represents each and every game state as numerical features, which will later make the training more efficient and a lot faster. Next slide. Now, the learning model used in the paper is a MLP, and instead of manually programming things such as there's a barrel jump and all of that, we let the network learn and take decisions on its own using the training data. Now, the MLP takes in 551 input features which describe the current state of the game, like the position of Mario and the barrel surrounding it and all of that. Now it processes all of this data through one or two input hidden layers and then processes it to two outputs, which would be the actor head and the critic head. Now the actor head would be the one that chooses the action for the particular state, and the critic which will be the one that evaluates the current state. Next slide. Now the actor works on the policy structure, which selects the action for the given state, while the critic works on the value structure, which evaluates the actor's chosen state for that chosen action for that particular state. Now, both the actor and the critic will take in 551 inputs and process it, while the actor will have seven outputs, which will be all seven possible actions for Mario. While for the critic, it would predict how the what the value of the current state is, and during RL, the critic computes the temporal difference error based on the actor's previous and the current decision taken, and it would tell how the decision made better or worse, made the outcome better or worse. And before the RL part, we first train the model using LFT, which would be the imitation learning. So we basically the player state and the action for each and every state is logged in as pairs, and we build a data set. And later we use this data set to for the supervised learning and train the actor network. Now, after training this MLP, we good to go for the reinforcement learning, because this itself is becomes a good starting point for the RL before the RL. And with the what is that with the LFD itself, we get a 56.6% of win rate. And now in the RL phase, now in the RL phase, the agent interacts with the environment with the action it chooses for the particular state. Now, the environment responds to it with the next state and the reward for that state. Now, it works based on two functions, that is the policy and the value function. The policy function is the one which maps the states to the action, while the value is the one that estimates the expected future rewards from the state. Now, the overall objective is to maximize the total rewards over the longer run than to focus on short term rewards. And this allows the agent to constantly improve its policy function, making it constantly better.
Okay, so after going through the paper, we decided to go about the project in three different stages. That is the game engine, the feature extraction, and LFD, and the RL part. So this week we worked on the game engine part. So I will be diving into that one right now. So in the game engine, one of the core parts of the game engine is the game loop. So what the game loop does, okay, essentially a game is nothing but a bunch of frames which keep repeating itself a bunch of times per second. So the each frame is dictated by this sequence of events. So we start by initializing all the window, the images, the width, height, everything, all the booleans and etc. Then we move on to the while loop, which asks whether the program is still running or not. If it's false, we quit the program. Otherwise, we go towards handling the events. Events are nothing but inputs which are given to the program by the OS or by the user itself. So it could be quit, it could be keyboard presses, timer events, mouse clicks, etc.
Then we go to update the state. This is where all the movement and all the collision checking etc happens. And we move next, we draw all the updated images onto the screen, and then we move on to the tick clock. Tick clock is used to set the FPS rate. And if we don't have the tick clock, that would mean that the game would run faster and more better on better CPU than if this is present. If this basically makes sure that it's all equal. And flip display is used to move on to the next screen. So like it keeps changing between two screens. So the current screen is the one which you're seeing. The next screen is being drawn in the background, and then they swap when this is called. So as for the game engine, this is what we were able to achieve in the past few weeks. We went for an object-oriented design for like better readability and maintainability. And we have two classes essentially, that is the Mario class and the Barrel class.
Mayur, we can't hear you.
Someone help Lord?
It seems like Mayur is having some internet issues. Let's not delay this any further. If it's possible, can someone else screen share and continue?
Do that. Give me a minute.
Sure.
Hello.
Yeah. Hello. We can hear you now, Mayur.
Okay, I'm so sorry. I'm so sorry. My network had some problem. Wait, I'll get back to presenting. Wait, are y'all? Should I press continue or are y'all move? Have y'all moved?
Yeah, try continuing.
Okay, thank you. Oh, yeah. So we were covering about the Mario class. We were about the reset is the method which is used to set all the game parameters back to the initial state whenever a life is lost or when you want to restart the game. Update is where all the movement and drawing happens. So in the update, the horizontal movement, the vertical movement, the jumping, gravity, everything is handled by the update method. Next, we have the barrel class, which is nothing but a child class of the pygame.sprite group, which is uh, which is useful when we have to handle multiple sprites and treat them the same way. So we have the update, which handles all the movement as just like how it was done in Mario's case. Check collision with bridges, which makes sure that the barrel is on top of the bridge and doesn't fall through it or something. Check collision with ladders, which introduces the 50% chance of rolling down the ladder and stuff. And then we have the demo. I hope it's visible to you all. So this is what the gameplay looks like currently. We have introduced 3 lives, and currently the scoring system is 100 for jumping over the barrel and 1000 for winning the game. So yeah, that is what we were able to make till now. Next, we have the problems we faced while building this. Out of the many problems we faced, the two major ones were the bridge collision and the ladder detection. So as for the bridge collision, one of the problem was the snapback. That is, what used to happen was Mario would go halfway through the bridge and then he would get snapped back onto the bridge, rather than just standing on the bridge. So the reason why that happened was because our collision check was after the movement. So we made that swap and that fixed the problem. And another one was mix up with the ladder detection. So that would mean that whenever Mario used to climb down the ladder and come here, he couldn't escape. He couldn't move horizontally over here. The reason for that being we used overlap checking. So he was technically not overlapped when he was standing over here. So to fix that, we introduced a small ground probe which has a small minute tolerance, and that fixed that one. Next, we had the ladder detection problem, which was we used overlap to detect the ladders initially. But the problem was that when he was standing on top of the ladder, he was technically not overlapped with the ladder, so he couldn't use the ladder at all. So we fixed that by introducing this one, which is nothing but it checks the center of the Mario sprite and center of the ladder and makes sure that it is within a range. And using that, we were able to fix this bug as well. I'll be handing it over to Pranavika now.
So our next step would be to implement the feature grids for feature extraction. So the first one would be the vision tracking grids, which are two 7 into 7 grids which move along with Mario. And these grids are to track the barrel and the ladder positions. And only the grids with the barrel or the ladder would be set to 1, and the rest would be set to zeros. So each 7 into 7 grid will give 49 Boolean inputs. And so there are two grids like this. And after this, we'll also be implementing the agent tracking grid, which would be to track the Mario's position in the entire game frame. This will be a 20 into 20 grid, which will span over the entire game frame. And only the grid with Mario will be marked to 1, and all of the rest will be set to 0. So this would give the absolute position of Mario in the game frame.
And this will give 400 Boolean inputs, and later we'll be using these inputs to train the network. Next slide. So for the next week, our goals are to complete the feature grids and then begin the feature extraction by recording the gameplay as state action pairs. And then we build the supervised learning dataset and finally start training the MLP using the collected data. And yeah, that's it from Team Barely Learning. Thank you.
Are there any questions? Guys, you have a question in the chat.
So right now we've been researching on only how to create the data set, on how to implement the grids and all of that. Feeding into the neural networks, we'll be thinking about it in the later part. So right now it's to implement it through Pygame itself with the only with the feature extraction part we've researched about. So the input part we'll be doing it later. Thank you.
Okay, I'm guessing there are no other questions. If you guys do have any questions, be sure to put it in the chat and they will get to you. We can move on to RepoLens.
So, good morning, everyone. This is Prajwal from Repolens. And due to unavoidable circumstances, Harsh, my teammate, is not able to join. So, let's begin. This is the third weekly update of our project. So, RepoLens, to begin with, is an intelligent repository understanding system designed specifically for large code bases. The goal is to help developers ask natural language questions like how does the authentication work? Where is the API implemented? Which modules depend on which file? Instead of manually navigating hundreds or thousands of files, this will solve these issues. But then again, RAG pipeline for code bases, yes, but this is not a traditional RAG systems because traditional RAG systems work well for documentation, semantics, but source code is highly structured. So breaking code into arbitrary chunks often destroys important relationship between the functions, classes, and files. So instead of treating code as plain text, RepoLens first understands the repository structure, builds a structural representation of the code, generates summaries for individual code entities, and later retrieves context using that structure before sending it to LLM. So as per the okay. Um, the first implementation improvement of this week was batching our LLM calls. Generating one node summary at a time resulted in a large number of API calls and unnecessary overload, and it was much expensive. So we redesigned this process to batch multiple nodes together, significantly reducing the time to validate while improving overall throughput and reducing the latency. The second major milestone was implementing a fast packet. So instead of running every everything as one script, we modelize the project and the pipeline into independent API routes. These routes now handle repository cloning, node extraction, tree generation, summary generation as separate stages. This makes the system easier to debug, extend, and eventually integrate the front end, which will be a part of next 2 weeks. So now my teammate Ishan will explain the later parts of this week's progress.
Can we go to the next slide? Yeah, so our system was actually specialized for programming languages like Python, but we extended the support to other languages like HTML as well. And after that, we did dynamic creation of graph based on the available nodes. So what the tree sitter does is it identifies the nodes, and these nodes need to be uh, given a summary, and the relationships needs to be shown. So in this diagram here, we can see that there are nodes that have been represented, but only representing the nodes is not enough. We need to show the relationship between them. But if we directly try to process the code base, it is very easy. So we are basically explaining what each node contains. Each node contains the ID, a specialized ID, and it also contains the relationship between each node. So what we do is we show the relationship between each other. In this diagram, you can see that it is color coded so that programmers can understand it easily. The green color represents the files, and the purple and the blue one represents the folders, and the orange one represents functions and other details. So this is a very simple code base, and it doesn't have much interdependencies. But other code bases which are complex will have function calls and class inherits and all of such things. So it'll be bigger and more messier. So this is how the graph is supposed to look like. But the LLM does not exactly see this because the nodes itself have the parent ID and the child ID through which it can access what the children are, and that's how it processes things. Now, Anish will be explaining the nodes and all of that through a demo. I'll hand it over to Anish.
Hello guys, Anish here. I'll be walking you guys through a demo of what we have achieved so far. First, we do spin up a Ubicon server, as you can see here. Then we go on to clone the repo by going to slash repo. We send a post request there to that route. As you can see, I am putting a real repo for sample source on GitHub. Contains a lot of HTML files, which is what would be ideal for a use case. And as you can see, we do get a success message. It's cloned at this part. You can see, as you can see, the output folder it is found. Then we go on to send the post request that trigger out, which generates the file tree structure, all the files and folders in the repo. So give a success message. As you can see, we have all the files, the folders along with their nodes. Represent the code segment of that particular file. Various node IDs. Now we'll be creating the nodes itself. Nodes, as I explained previously, as a code segment or code snippet of each file. And this gives a success message. And when we go to the output folder, we have the nodes, a node.json file. The good part of this, it gives the language, it gives the node type, and even the parent. It will have the summary in the next step. This summary is merged with the file structure summary, which provides insight into a whole folder of file and even the repo. Now, when we go on to the summary route, a post request is sent. It then is a summary for this. We did implement matching, which was done in the past week, to make it more efficient. As you can see here, we do have summaries for each and every element of the code. and you have children IDs for each node, and even which represent each part of the code base, and summaries for all the children also, all nodes. As you can see, it works for all the code files. Next, I'll be walking you guys through the next steps of our project. Currently, we do get the nodes.json, the file structure of JSON. But to satisfy the user's question, we need to select nodes which are relevant to their question. This is done using semantic search, which uses the cosine similarity uh, part of scikit-learn. As the vector database goes, we use Quadrant. It's going to be locally, not on the cloud. And for the embedding model, we'll use Gemma embeddings because open source and it will be cheaper for us. And I want to add one more feature. We would want to select nodes by name. For example, user asks, I want this function name. We just need to retrieve that particular node. So it doesn't make sense doing a semantic search when you want for exact particular name. So we'll be implementing a system to achieve that. Thank you.
Hello, am I audible?
Yeah.
Yes,
Yeah.
yes, you
I
are.
have a bunch of questions. Is this the right time to ask it?
Yeah, go ahead.
Yeah. Okay. So first off, I'm a bit unclear. So there's a part of your slides which told about how you reduced LLM calls and how you're
Yeah,
kind
yeah.
of trying to build an index for trying to make the LLM traverse your code base more efficiently. But also you talk about using cosine similarity and like a search query. So is the LLM calling the uh, cosine? Like, is this part of the call flow? Or like,
No,
how
no,
is
no,
it?
no. So we generate the summaries for every particular node using the node's content, and that is batch because you can't just give a code block with 3 lines and ask for a summary because we are not that rich to afford for every API call. So we
Right.
batch 20 of those requests or 20 of those code snippets to get the summaries of 20 of them. And
Yeah.
the classic RAG, the summaries, the semantic search works on these summaries which are generated. So if you
Got
ask how does authentication work in this particular repository, it will take the authentication word, it will compare with the embeddings of the summary embeddings, like whatever every summary
Okay.
we have. We have node level summary, we have file level, folder level, and even the parent summaries as well. So it will do a semantic search over all these summaries and then get you which nodes are very relevant. So then we'll make a re-ranker. We have a re-ranker which will rank the top 5 nodes and then get us the node content as well, so that the LLM will have total context.
Got it. So you're only
Also, we'll
calling the
just
LLM
parents
during.
also because each node has a parent field. So it will be more. It's a dependency also between the nodes.
Got it. So you're only calling the LLM during build time for the summarization. Is that correct?
Yes,
Ah,
yes,
yeah.
yes. During the build time and
Okay.
later, yeah.
Okay. And when you want to like say search for like how does auth work, right, in your code
Yeah,
base, is
yeah,
this
yeah.
like a pure RAG or
It
is
will
your
be a
LLM calling
see,
this
see, see.
part just to.
Yeah, we have a query classifier coming up in the next week work. So query classifier will have two pipelines. One is the normal semantic search based classic RAG pipeline, which works on summaries of the generated nodes, and the second pipeline
Okay.
is the exact keyword match. So when you ask for a particular function name, like if you ask particular function named Hemant or something, then it will do exact match with the node titles, like maybe BM25, and get you the chunk. And once you have the node, like Hemant function node, so it will have dependencies, it will have function calls inside it. So those all will be linked with the parent IDs and the children IDs. So we will bring all those together and give it to the LLM so that it can have the total context and answer you properly. So these are the two pipelines which we have proposed. And maybe if we have other pipeline requests, maybe based on the different type of questions which can be answered, we will also plan on implementing two more other types of pipelines.
Got it.
Yeah.
So my one suggestion would be, as part of your like eventual testing and stuff, right? So if you take something like Copilot or tool-based LLM right now, even
True.
for very large code bases. I've seen them do like a really good job with the same problem that you're solving. However,
Uh,
they take a lot more tokens,
true.
right? So
True.
you are kind of, you're not really competing for performance, you're competing for cost savings. Would that
Yep.
be an accurate way of phrasing?
Yeah,
So
but they
so
does give good performance also because
the
we get
main
only specific
priority.
nodes.
Yeah. Let me
Could you
go.
repeat that? Both of you were talking at the same time.
Yeah. Yeah. So yeah, the main priority of Repolens is to give developer a local only tool through which he can get parts of his codes summarized, like to understand what his code does. So we use tree sitter, which will actually identify the functions in classes by itself. So no LLM calls there. So it is an efficient
Okay.
way to understand your code base, not to, Copilot and all, you'll have to feed in the entire file. Entire file maybe
Yes.
3000 lines and everything. So that will
Yes.
be costlier. So instead of that, it is a cost effective solution for understanding your code, not to
Got it.
reason on the code, nor to develop, make it more further or vibe code it. This is basically to understand about how your code is, where what stuff happens, and how are they connected with each other, what imports what. It is mostly a repository intelligent software rather than a coding assistant or maybe something like that.
Makes sense. So it's mostly, is it intended to be used with a local LLM instead of a
No,
API
not
called
local
LLM?
LLM, but we can't host it, right? So we can't give you API call. So this will be a project which you
Got
can use it with any other API. Yeah,
got got it.
yeah.
So the thing is, you guys, okay, that makes complete sense. Thank you for the explanation. You guys spoke about how your guys are doing batching to kind of reduce the request
Yeah,
cost, right? But now that everybody is moving
yeah,
to
yeah.
token based pricing, do you think that is a worth optimization, or like the savings are there even with that too?
Latency. What about that? Thousand. We will have more than 1,000 nodes and 1,000 AI calls. That will be a lot of time spent in generating summaries.
Fair enough. Yeah, that makes sense. That's
Yeah.
a good use of the batching.
Yeah.
My last thing that I wanted to understand was that, I see that you guys have developed a fast API for it.
Yep. Yep.
I wanted to kind of understand what is like the use case for which, this
Because
is being managed by a, yeah,
yeah, we need a front end for question answer based chatbot kind of interface as well, no? So the only way we could do this by serving an HTML is by a server. So we had a Flask or Fast API, so we chose Fast API.
got it, got it. And does your API also allow not, does it assume that the cloning is done by it, or can I provide
You can either provide a
the,
local repository or you can also provide a GitHub repository link.
okay, makes sense.
Yeah.
Got it. Thank you so much. That makes sense.
Yes, welcome. And about answering Anthik Vijay's question, when batching LLM calls for efficiency, what happens when one call is dependent on the previous call? We have children IDs. I mean, we are just getting the summaries of every particular node. So if there is a function, I am just asking the LLM to summarize the function for me, and the context or the dependencies is all preserved by the children IDs and the parent IDs which we have. Like they all contain the import statement about who is calling whom, which class contains which methods and functions, for example if you're speaking about Python. So all of that is preserved in the children IDs and nodes. So context will preserve nevertheless. So when you ask for a method which is hidden in a function, hidden in a class of any folder, the moment the we identify the node, we can call every children and every parent belonging to it and get the context. I hope that answers your
Mm,
question.
I would say one interesting thing you could do with this project, right? I know it's not in scope, but you're mostly focusing on like trying to locally understand the code base, right? But like
Oh
a
yeah,
Yeah,
lot of people who use like Copilot to do the same, the agent kind of like, it does like command calls of like a find this keyword and stuff, right? To try to traverse the code base. I think you have a much
yeah.
more efficient way of traversing the code base. That just if you can like expose it as like a tool call, even for people who are using their own copilots or whatever,
Yeah,
it
yeah.
would be like a much more efficient way and like cost saving way to traverse the tool base, because now you're not parsing large files or running commands, which are at the end of the day slightly riskier. So yeah, that's just something interesting I thought that would be
And we
useful.
could use MCP or something. Yeah.
Yeah.
Yeah, like NMC. Yeah.
Yep.
Anything which I know, we are not passing all the children IDs for context. When we actually, like, when you ask a question, how does authentication work? When it actually finds which node contains authentication, that particular node has children IDs and the parent ID as well. So then we will take all those children IDs and give it to the LLM for answering. So I think Anish can show us the JSON much clearly.
And just
Go where you're zoomed into the JSON, like it was in the middle, much further. Yeah, here somewhere. Next, next, little bit. Yeah, open it. Not the file structure. Go for nodes. Go for nodes. Yeah, and full screen it. No, full screen it. You have an option to the right side. Yeah, pause here. Pause here. Pause. Yeah, you can see ID, which is a unique arbitrary ID given. You can see the path. We are changing it to a relative path. Language, node type, title, start line, end line, and the summary. Summary will be populated in the next call. Like we have a function, we have a new
Yeah.
endpoint for it, and the parent ID. Can you scroll down? Like maybe resume the video. Resume the video.
Got it. You have this like tree like structure, which is
Yeah,
very useful. Yeah, that makes a lot of sense. Uh,
true, true.
do you have like a list of children there? Is it just printed?
Uh,
विशाल रे इथं कनेक्ट होलाय तुझं तुझ्या इथं केलं कनेक्ट होलाय बंद कर
Hey, sorry, I had Bluetooth issues. I'm audible?
yeah, you are.
yeah.
Yeah. 1 second, sorry about that.
So you can see the chat. I'll just send one more of my project which I had run on. This is just a HTML file, I guess. So mine is a Python project, so you can see it
Good.
on how it
I
works.
can't. Yeah, no, no. Oh, perfect. Understood. Thank you. Yeah. Good clarification question.
So
I think this
there
is
are different types. We have, yeah,
makes sense. Okay, makes sense. You have predecessor and the children.
Yeah.
Okay, makes sense. Good work, guys.
Done.
If there are any other questions, we can take it in the chat and we can get to it later.
yep.
We
Thank you.
can move on. Yeah, we can move on with silicon.
Is my screen visible?
Yes, it is. You can go ahead.
Okay. Good morning, everyone. Welcome to Silicon, where we explore silicon through synthesizable RTL, register transfer level simulation, and open source tools. So, I personally have chosen to depict a kaleidoscopic visual using Verilog, and this is my progress so far. So, talking about week two's progress, my primary focus this week was establishing visual balance and interactivity. I started by building a symmetrical pattern grid layout to ensure the foundation was structured and aligned. My left and the right states, I designed a button that cleanly toggles and swaps the design's color palette. This brings both symmetry and functional interactivity to the design. Now, talking about the overall logic flow, this process starts by locating each pixel, shifting its coordinates to the screen's center, and then applying symmetry logic to mirror the image. And then after that, for the button, it uses a time-based counter to create geometric patterns in motion, looking up the appropriate color for each section before sending the final signal to the monitor. As we can see in this diagram here, the clock signal just checks the frame completion. If it's a yes, then it increases the frame counter, and we see the different like we switch the colors here, right? So it's the different frame. And if it's a no, then it waits for the next clock signal to happen. Moving on to week three's progress, my main focus was breaking down the design to make it easier to work with. So instead of building the entire screen of image all at once, I started by using Verilog to just design 1/8 of it. So as we can see this triangle here, this is just 1/8 of what I was building. So by building a small slice, I can just repeat the pattern and build something like this. So by taking that 1/8 section and increasing the axis of symmetry, I mirrored it horizontally, vertically, and diagonally, and I flipped it and repeated the pattern across 8 identical regions. So in Verilog, this means we only needed to calculate the logic for one piece. The hardware then automatically reuses and mirrors these coordinate calculations to generate this entire seamless graphic. Uh, Talking about the logic, so by mirroring any negative values into positive range, the system first creates four identical mirrored quadrants across the horizontal and vertical axis. It then compares the coordinates within each quadrant to reflect the image along the diagonal lines, resulting in 8 perfect triangular slices. So in this diagram, it just asks where the pixel is. Accordingly to the answer, if it's a yes or a no, it shifts the pixel, and if it's a no, then it keeps it as is. So this creates that first four-fold symmetry, but later on, to make it eightfold symmetry, we use the y coordinate and the x coordinate logic. So if it checks if it's greater than x, then it reflects along the diagonal. Otherwise, it keeps it as is. So this creates the eightfold symmetry as we saw here. So talking about the motion and frame control, this is what makes my visual moving. So the hardware really just tracks how many full frames have finished drawing and increasing a simple counter every time a frame is complete. So this counter's value acts as a changing offset that shifts the pattern's mathematical formulas over time, which creates the smooth progressing pattern as we can see in the next slide. So this is what I worked on this week. This is how the pattern looks like right now. I still have to implement a few other things. So yeah, moving forward to Kritika's work.
So project I'm making is evolving tiled patterns. So just to quickly recap what I worked on last week, the main focus was on building the basic concepts that I need for this project. I created the tile pattern, explored different distance metrics for generating shapes like diamonds and circles, and I also tried a simple shape morph between them. So, building on those concepts, this week I started working on the first stage of my project, which is the animated triangle C. So, this slide shows the overall animation sequence for the triangle stage. The entire animation is controlled using a single frame counter. As the frame count increases, different animation stages are triggered one after another. So the triangles first grow, then they start pulsing, followed by a traveling wave. Finally, horizontal motion and a rainbow color transition are introduced to make the feel more dynamic. Could you move to the next slide? So the first step was generating the triangle. Instead of using an image, the triangle is generated procedurally inside each tile. So basically, the width increases from the top towards the base, which naturally forms the triangle shape. It's all about deciding if a pixel should be colored or not. So conditions and comparisons are used to create the triangle boundary. Since the same logic is reused every frame, only the triangle size needs to change later to create the different animation effects. Next slide, please. So once the triangle was generated, the next step was animating it. Triangles first grow until they reach their full size. After that, their size keeps changing to create the pulsate effect. So the frame count is used to generate a value that increases from 0 to the maximum value and then decreases back to 0. So a small timing offset is then introduced between neighboring columns. So different columns start the pulse at slightly different times. So instead of every triangle pulsing together, the pulse travels across the screen like a wave. Next slide. The last step was to add motion and color to the scene. So a horizontal coordinate shift makes the entire tile pattern move together smoothly across the screen. So for this, a drift counter is used to keep track of the horizontal offset within each tile. So then moving color bands are used to gradually change the triangle colors, creating the rainbow transition. This uses similar logic as the drift, but it directly uses the animation counter since it only needs a simple increasing offset. Since these effects are added independently of the triangle shape, the same geometry can be reused throughout the animation. Next slide, please. So this is the current output of the project, as you can see on the screen. It combines all the animation stages that I worked on this week into one continuous sequence. It starts with the triangle growth, followed by the pulsating effect, then the traveling wave effect, the horizontal motion, and then finally rainbow color transition. So all of these effects are driven by the same animation timeline. So the scene progresses smoothly from one stage to the next. This brings together all the concepts I explored this week into a single continuous animation. Yeah, these are our goals for next week. We'll first finish any remaining parts of the project and combine everything into one clean and working version. Then we'll test and design throughout the thoroughly fix any bugs or edge cases. And then we'll update the documentation and make sure the project is ready for the week 5. Thank you.
Are there any questions? Okay, it does not.
If we have
Sorry.
no questions, I think we could go forward with graffiti.
Am I audible now?
Yes, you are.
Okay, I'm so sorry about that. Um, Hi guys, so I'm Sanidhi, and I'm here with Team Graffiti with my fellow mentees Narendra and Arna, along with our mentors Arvind and Atharva. So, what is graffiti? At Graffiti, we primarily aim to explore graph neural networks and how they work, along with where exactly graph neural networks fail. So, based on these limitations that we found from our previous experiments on graph neural networks, we also aim to explore some alternatives, such as a graph pattern machine, and also implementing a graph pattern machine from scratch. So, going into GNNs and their limitations. So, a GNN primarily works through message passing. This means that each node collects information from its neighbors and then updates itself. This means that a GNN is mathematically limited to something known as a 1WL test or a Weisfeller-Lehman test. This means that even with the best GNNs, if the 1WL test cannot detect a motif or a substructure, it means that the GNN cannot either. So with GNNs, you end up missing key substructures such as triangles, cliques, rings, etc. This also means that because it collects information neighbor to neighbor over a long range or over multiple layers, the information gets diluted. This is something known as ore squashing. And this also means that if you want to scale your model, this doesn't give you as accurate results as you would want. So, when we're talking about GPMs as an alternative, a GPM doesn't fundamentally has a different method of working. Instead of aggregating information from its neighbors, it goes on random walks around a node and it treats these walks as patterns. This means that each pattern from these walks gets encoded directly and sent to a transformer. This transformer runs across every single sample pattern and then figures out which pattern we need for the task at hand. This means that a GPM is not bounded by a 1WL test and which means that it can easily detect substructures such as triangles, benzene rings, and other cliques. This gives it better long range dependencies and also allows our model to scale better.
Okay, so the pipeline mainly has three stages. Stage one is a random walk tokenizer. So what happened here is it samples the substructure patterns and it can be done per node, per edge, or for an entire graph also depending on the task. The stage two is the encoder pattern encoder stage where uh, it takes the sampled patterns and encodes it into a single dense vector using a sequential model. So a whole walk becomes like one embedding. And stage 3 uses a transformer attention to look across all the sampled patterns for a given instance and figure out which ones actually matter for the task. And it also helps in reducing the noise and redundant ones. Moving on to our progress this week. So the pattern tokenizer. Diving into it. So the graph is stored as an adjacency list built using a default depth of list function from the edge index. So the tokenizer loops over which nodes we are generating patterns for, and for each one, it generates a fixed number of walks. So let's say if you want to generate 100 of a walk, the next neighbor is picked at random using the torch.randint function to do the sampling. Um, Also, one edge case that we discovered here was if a node has no neighbors, that is a 0 degree 0 node, the walk cannot move forward. So in that case, it falls into a self loop, just staying on the same node, which keeps every walk the same length regardless of where it started. So this uniformity and like continuity matters because in the next stage, that is the encoder stage, we expect a fixed size inputs for the encoder and finally, Once we have a walk, we index directly into the node feature matrix using the node IDs in that walk. And the output that we get here is a pattern tensor, which is then uh, forwarded to the encoder. Next. So the tokenizer output. So here we just validated the GCN limitations that we listed in week 1 and did a small toy experiment in week 2. So here we tested the same two graphs on our 1WL indistinguishable test that the GN and the GCN failed. So the question here was, can the tokenizer pick up the difference that the GCN couldn't? So it did, and looking at the anonymous paths for the two triangle graph and the hexagon graph, um, we can see the two triangles seems to be pretty short, repeat heavy, and the anonymous path looks like 0, 1, 0, 2, 0, whereas hexagon is longer, non-repeating paths and looks like 0, 1, 2, 3, 4. So the difference is exactly the point here. The structural information purely about the shape of the walk, and the tokenizer captures it like naturally, and but the GCN can't even access it. Yeah.
As my teammates had spoken, am I audible?
Yes, yes,
Presuming I'm
you're
audible.
audible.
Yeah, thank you.
Yes.
So, given the fact that my teammates had spoken about the current architecture up till what we've implemented, that is the random walk tokenizer, the next step would be the sequential encoder, as in we would have to take the output of the random walk and the output of the anonymous walk that is generated, and then convert it into embeddings. Given that we have the graph nodes here, so we just convert it into the embeddings, which would then be processed by a neural network. Post which, in the next stage, which is the transformer attention, we would basically receive the encoded patterns and then run self attention over the patterns that have been encoded, which would basically determine what would be the top or the top k number of patterns that would be required for running the ngpm. So this would help us perform the node edge or graph level prediction after the process with the transform attention at the task head. Next slide. So with the pattern encoder, like I said, we're converting the semantic and the anonymous walk sequences using the encoders. You might ask what encoders have the canonical NGPM paper used. So currently with the NGPM paper, they've used the transformer and the GRU, the transformer for the semantic embedding and the GRU for the anonymous embedding. So the transformer is basically here because we've gotten a particular sequence of nodes. The transformer would help determine what would be the relationship between the multiple nodes in the order that we've received, and the GRU is helpful in determining for smaller number of sequences, for less detailed sequences, because it's an anonymized sequence and doesn't really contain information about each particular node, but rather about the entire topology. So the canonical paper uses transformer and GRU in this regard for two different purposes. Though it might be interesting to see what other encoders might be used and which can perform a better which we can also turn into a learnable function. That could also be an interesting part that we could dive down later, given enough time. So the fixed size pattern is determined from the combination of these two embeddings, which would then be used for the pattern aggregation transformer to then determine the required number of patterns in order to generate any classification about the nodes and edges. So that would be the next task we would have at hand after already implementing the tokenizer. So yeah, that covers the majority of our work. Thank you.
Are there any questions? Okay, I think that means that there are no questions. We can move ahead with Twix.
Where is my screen visible? It's visible. Hi guys, we're Team Twix. I'll be running you through what we've been working on for the past week. So before, can you go to the next? Before training the model, we first needed a data pipeline which we've been working on. This data pipeline is responsible for preparing the images. The complete self-supervised learning pipeline has three major parts: the data pipeline, the model, and the loss function, and each has a different role to play. The dataset would read images from the dataset one at a time, and then applies pre-processing and data augmentations to create different views and representations. The data loader then shuffles these images and then groups them into mini batches and feeds them efficiently to the model. These pre-processed batches are passed to the encoder, which then generates feature embeddings. This would then be used to calculate the Barlow twins loss number. Go to the next slide. We're particularly using the STL10 dataset, which contains unlabeled images. So the model actually learns without using class labels. For every image, the get item function loads it and creates two different augmented versions of the same image, which we call representation 1 and 2. These augmentations could include cropping, color jittering, horizontal flipping, or grayscale conversion. Helps the model learn features that stay the same even when the image actually changes. The data loader then shuffles these images and groups them into mini batches and loads them efficiently. Sinchana will be continuing. Sinchana, we can't hear you.
Yeah. I'm so sorry. So I'll be explaining the model part. The augmented images that we got from the data loader is passed on to a model. A model consists of an encoder and a projection head. Here, encoder is a convolutional neural network that extracts the features of image such as edges, corners, colors, textures, etc. and produces something called a feature vector or embedding. And here we are using ResNet 18 as our encoder, from which the last classifier part is removed. In short, ResNet 18 has a CNN architecture and has 18 layers. ResNet stands for residual network. It uses residual or skip connection to overcome the vanishing gradient problem, which is seen in many deep neural networks, and it helps us train the model efficiently. In So the working of ResNet 18 is something like this. If I take x to be the input of this block or input to the block, and f of x is the features that is learned by the convolutional layers, then instead of just learning output is equal to f of x, the model learns output is equal to f of x plus x. So it has a memory of whatever that has happened before as well. So that is why it is more efficient than others. uh, the embeddings are later on passed to the projection head. Projection head receives the embeddings from the encoder and maps it into a new representation space to which the Barlow twin loss is applied. It is a multi-layer perceptron, which is again another artificial neural network which has linear layers in contrast to the CNN that was used in the encoder. So basically, the projection head
It will modify the embeddings in such a way that it is easy for the model to apply the loss function and to train it. And it serves only for this self-supervised learning objective, and hence it is discarded after training. To understand it more efficiently, we have an analogy. If encoder is like our brain which is trying to learn the concepts, and projection head can be thought of as rough paper where we try to memorize everything, like solving practice problems, and Barlow twins loss is our teacher checking those rough works and giving their feedback to us.
As I already mentioned, the data loader returns two augmented versions of the same image, Z1. After getting the augmented views, we then generate embeddings, which are Z1 and Z2. Then a cross correlation matrix is computed, as you can see on the screen. So the loss function majorly consists of two components, which is the invariance loss and then the redundancy loss. The invariance loss comes from the diagonal elements. The diagonal elements represent corresponding features from both the images, which means that the values of all the diagonal elements should be closer to 1, which shows that the model is learning the same corresponding features from both the images. The off-diagonal elements represents the relationship between different features of both the images. So ideally, this should be as close to 0 so as to prevent redundancy. Because if this is closer to 1, it would mean that the model is learning the same information as the corresponding features, and then there would be no point of having those values in the matrix. So after adding these two terms, we get the final loss value. So the formula would be invariance loss plus lambda of redundancy loss. So lambda is a trainable parameter. In our code, we use the value 0.005 to be able to ensure that both the redundancy loss and invariance loss have an equal weight in the final loss function, because the number of diagonal elements are much than the number of diagonal elements. So to ensure that the redundancy loss doesn't take over, we have that formula in place. You can go to the next slide. I'll be talking about the training loop and the testing harness, which we've been working on for the past week. So once the pre-training is done, we've used backpropagation. Backpropagation calculates the gradient of the loss with respect to every trainable weight. And then we use an optimizer. So the optimizer updates the encoder weights using the gradient descent rule. The formula is visible on the screen. Eta here in the formula represents the learning rate. So the original paper uses ImageNet as the dataset and uses LARS optimizer. So that stands for layer-wise adaptive rate scaling optimizer. That usually works with huge batch sizes. Since we're working with a much smaller data set, which is STL10, we've chosen to work with the Adams optimizer as of now, since it would converge quickly. Coming to the testing and training loop, once the pre-training is done, the encoder is frozen, and we then switch to the evaluation mode. Our labeled images are then passed through the frozen encoder to extract the feature embeddings. A single linear classifier is then attached on top of these embeddings. While using only the classifier's weights, which are then updated while the encoder remains frozen. So the classification accuracy is essentially the quality of the features which are learned from the encoder. So the higher the accuracy, it means the encoder has learned much more. You can go to the next slide. What we hope to do for the next week would be to link both the training loop and the testing harness to each other and actually experiment with more hyperparameters and essentially link all the blocks of code we have done so far. Thank you for hearing us out.
Are there any questions? Okay, I guess we can move on to Mushroom. If there are any questions, you guys can put it onto the chat and they'll get to you.
Am I audible?
Yeah.
Okay, thank you. Good afternoon, everyone. We're Team Mushroom. I'm Ananya. We project focused on user feedback. Next slide.
You're inaudible right now.
No, next slide, next slide. Just a quick recap. The chat server that's directly accessible in your terminal with a connection that's such flow. You do not need to download any extra apps like you do with say. But just enter the required command. We'll straight up enter a server with many other users along with you. Chat with. Our inspiration for this was Shazam's SSH chat, which we talked in detail about in our week 1 review presentation. We aim to sort of replicate this and add in our own features along with the cool UI. To implement this, we will be using more particularly its bubble tea terminal UI shape, the wish trick, which is specifically made for creating SSH servers for terminal. Other than mentioned SSH, let's talk about what it is. Its core form is secure shell protocol. If you want to connect to a system, like say running commands, when you do it over the internet, your data could pass through many networks and can be insecure. It can be viewed native and modified before it reaches a packet. Now, SSH protocol directly connects your device to a remote server safe, where you can run commands with no interception. To make the connection, all you would have to do is enter the command SSH user at server host to your terminal. Our server host can either be the domain name or the IP address where the required SSH server is stored. User access to the SSH servers can be authorized using either a password or a key pair method of authentication. The key pair is what we'll be using. An SSH key pair has two parts, the public and the private key. The private one remains on your local computer, and the public one can be given to other resources like the server you want to connect to or verify that this connection. Since our app is interactive, we need a particular paradigm that continuously updates the interface according to the user's actions, right? The Elm architecture is exactly that. It works like a loop with a unidirectional flow. It keeps updating itself based on the event triggers it receives from something the user does. This is used mainly in programming and is what we use here. The architecture is implemented with two main parts. The model is something that stores the current state for you. For example, in our chat app, every user session model contains information about the screen that they're on, their username, their user color, etc. This consists of update is a method that looks at what should happen and returns an updated model in response. For example, if we want to detect the key press that was made by the user, we have a space in our update method. It detects what key was pressed and makes the changes we need. Finally, the view function actually control view. Takes the updated model and based on the attributes of renders our UI with a bit of effect. Like I said, Elm architecture is what we use to do our interactive. The ability to look in code. This is the perfect platform to do that. This library is gloss glamour. It range of objects. Talking about Wish, the SSH server allows you to make apps accessible over SSH. There's a wide range of middlewares that allows us to define what the user can do. In our case, we use SSH and WP middleware to solve the problem. This process is very similar to a website. We're making an SSH app available and running on a certain port, and making the interface accessible to users. We have the SSH protocol backing this app, which makes user authentication very easy to implement with SSH. Let's talk about our progress. Focused on learning code from the ground up. Week 2, did our property. library and create our own note features like note saving and tabs to view multiple notes at once. Week 3, our task was to actually create the chat app with its basic features. Currently, the Wish server runs on localhost, but the app can handle multiple users, and we've implemented messaging in slash commands. I will go more into detail with this.
Okay, so I'll explain how the current architecture works. So, just for reference, model is basically the information that has yet to be rendered onto your screen. So, when a user joins the chat room via the terminal, the app will create a model and a program. This will be displayed onto the user's client, as well as it will return a pointer to the current user session into a slice called sessions, as you can see here. And this is all done by using Go routines. So when a user connects, a Go routine will be instantly fired, which will save the user session into this slice. So to ensure there's no race condition between Go routines, we use a thing called mutex. A mutex is basically a thing that blocks the Go routine. Like it doesn't allow another iteration of the Go routine to occur until the current Go routine is finished. So what would happen if you didn't use a mutex is a race condition. A race condition is basically two Go routines trying to modify data at the same time, which leads to data override, which will basically crash your program. So I'll break it down into parts. First up, the user sends a key input. This key input will be onto the view. The view will send this key input to the update. The update will process this, and then it will return an updated version of the model. This updated version of the model will be returned to the view, and the view will again render the same to the user, which shows a new slide. Okay. Yeah. Now, how do you get messages to be displayed across everyone's screen? So when a user types into a message, the view will take it in, and then it'll call upon a function called broadcast. So basically, what broadcast does, it sends a message of type chat message to each user and the programs. So it will send this into their model, and the view function will render this into their screens. So when a user leaves or enters a chat, it will display a system message using again the same broadcast command, and it will iterate to each user in the server and will display this command. So in the background, when the user leaves, another Go routine will be fired off, which will basically remove their pointer as well as their model and the program running from their end. This will save us the data in the slice, so we don't run into meaningless data. Yeah. So this is a screenshot. As you can see, only one command to enter into the startup. At first, you'll be greeted by a input box where you have to input your name. And after you input your name, you'll be viewing this screen. And you can see some commands we have currently implemented: help, user, emoji, colors, quit, user color. By using user, you can change the username, you can change the user color, you can even enter in emojis. So some of the challenges we faced. So we were not comfortable with the multi-user SSH environment. It wasn't just the model view update loop anymore. We had to make sure all the users between each SSH connection had the changes applied to their screens. And we also had to come up with the architecture that would actually make this possible. So we did this by using the middleware function. Middleware function basically runs a certain function for each user. And our middleware here is a bubble tea program. After running this function, it stores a pointer to this function in the slice called username, which returns the name of the user as well as the session. So we did this all using mutexes again, which fixed our race condition problem. And we also use basically using mutexes and middleware.
So up next week, we plan to continue building this out, adding the chat rooms feature that we mentioned before, more slash commands, and a few more UI components to fancy things up. We have a few ideas for refactoring as well. Like for example, right now it to store users as a slice, right? We kind of want to make it into a map because the slice contains structures right now which has username and a pointer to a program. We want to create it into a map instead with just username as the key and a T program pointer as its value, which in that case it would be more cleaner to code. Thank you. We'll be back with more cool stuff next week. If you got any questions, let us know. But we have a set of questions too that came to us when we were working on this. So do check these out. Yes, thank you.
See you guys in week 5, guys. Bye bye.